we've now looked at the molecular shape. We've looked at the issues regarding or surrounding how they look. We've looked at the gases. We've looked at ions. We've looked at dipoles. We've looked at all those things. And we've looked at intra and intermolecular forces, the van der Waals and all of that. So we've built up pretty much a repertoire or the knowledge to be able to tackle the physical chemical reactions themselves. The last thing that we need to just go through again is the concept of the mole, right? Now, the mole, as a concept, was we needed it, and if you just think logically, like we said before, you can mix a teaspoon of that, 2 cups of that, 2 tablespoons of this, a pinch of this. The other day I heard somebody talking about a glug of olive oil. I think Jamie Oliver's the guy who uses a glug. A knob of butter, all these funny measurements that we get in cooking, which in essence is chemistry, if you think about it, isn't it? It's chemistry and physics, applied chemistry and physics. So what do? We can't use, in chemical terms, we can't use a glug, right? We can't use it. We have to have a standard basic form of measurement for chemistry. Why? Well, if you remember, what did we say? We said that, okay, remember we had our nitrogen and it had 3 bonding spaces, right? Right. And we had our hydrogens coming along, NH3, 3 hydrogens. Each one was parking an electron into its parking space, which then was forming NH3, ammonia, right? Gas, or whatever we're going to do with it. But each single chemical reaction, each single chemical process requires us to account for each and every electron. Okay? That's basically the bottom line. Because we're not going to have electrons hanging around in a soup. Okay? They're going to go somewhere. Right? And if they ain't going there, they ain't going nowhere. Let's just take it at that for this point, or this part of the work. So we came up with something that links essentially all of the chemical reactions together, called the mole, right? And what does it say? It says, well, 1 mole of anything contains Avogadro's number of anythings, right? So what have we got? Put that on. 1 mole of stuff has got Avogadro's number, Na. I'm just going to write it down there. And let me just get it. It's is equal to 6,02 times 10 to the 23 bits of stuff. Right? So 1 mole of carbon, okay, 1 mole of carbon, for example, has got 6.02 times 10 to the 23, okay, atoms of carbon. 1 mole of nitrogen has got 6.02 times 10 to the 23 molecules. Okay? Therefore, 1 mole of nitrogen atoms has got 6.02 times 10 to the 23 atoms. Okay? Now, how do we convert? That's great, because now what have we done? We've now counted each and every atom. We've accounted for each atom, we've accounted for all the electrons, so everything is perfectly balanced. But we don't count atoms in a lab. We can't. We can't go 1, 2, 3. Okay, we'd lose count, number 1, okay, because there's so many. But it's impossible. So we needed some way to link up this guy to a certain measure that we can have. And basically, we then the scientists came up with a measure that relates the mass of the stuff to the moles of the stuff. All right? And what do we call it? You've done it previously, the molecular mass, right? So we've got something called molecular mass. Okay? And if you look, you'll see the molecular mass of carbon is 12 grams. Right? 12 grams of carbon is equal to 1 mole is equal to so many molecules, atoms, electrons, whichever way we want to go with it, right? That's why we do this, okay? Let's just recap. Let's have a look of 1 mole of H2. Now, hang on. We've got to be careful. H2 was what? Remember? Let's just go back. H2 was this guy over here, wasn't it? Okay? They were joined together, okay? Pure covalent bond, remember? Linear bond, right? So what do we do? 1 mole of H2, but now we say that has got how much? It's going to split, isn't it? To that. If you look up the molecular mass of hydrogen, you'll see it is 1 gram. 1 gram. So how much is in H2? We have to have these 2 hydrogens added. So it's 2 grams per mole. Okay? Now, where most of the students struggle with this section, and from here on out with chemistry, is the concept of basic ratio. Unfortunately, it's not mine to pass a judgment, but I find that not enough was spent on it, and it's kind of put in a situation as one of those things we've got to do, but it gets confusing at this point because we're going to be cooking with chemistry, right? We're going to be cooking atoms together, making stuff. It's a recipe. So we need to know how to use a basic ratio. For example, let us say that a basic ratio is 250 grams of A plus 500 milliliters of B plus 4 eggs, let's say, it's C, all right? And we mix that together and we get A. These are our reactants, and this is our product, right? Let's say it's a batter we're making or whatever, it doesn't really matter. But that there is a ratio. It is 250 as to 500 as to 4. Let us say that that is for 10 people. Okay? 10 people. But now we aren't having 10 people to dinner. We're having 5. So what do? That's for 10, right? So we need it for 5. So what do? We divide it by 2, don't we? We halve the recipe. So we go 125 grams plus 250 milliliters plus 4 over 2, which is going to be 2. So I was thinking something else at that point. I was just imagining if I had to put 3 there, then somebody would obviously say, excuse me, how'd you get half an egg? You don't. Okay. Suppose you could beat it and then halve it. Maybe. I don't know. But then that's for 5 people, isn't it? Can you see that what we've done is we've ratioed it up and we've ratioed it down? Okay. And I'm going to show you in the table method that we use to solve these kind of problems, the easy way to go about it. Okay. And it's a simple method. You have to ask yourself a question. Okay. As you go through. Am I going up or am I going down? Okay. So yes. We've now got this quantitative aspect to consider because we're now going to be mixing various chemicals with each other. Let's have a look. We've covered that. And the last thing, right, I said it last time, 1 mole of any gas at STP is 22.4 decimeters cubed. So if you've got 5 moles, you've got so many moles of that. Okay. Now, let's have a look at, sadly, this is the formula, but hey, mostly this is the one we're going to be looking at, right? Because it's very relevant to us, let's have a look. Let's look at mixing nitrogen gas plus hydrogen gas, okay? And we're going to get ammonia gas coming out this side. I'm going to put a double arrow there, don't worry about it at the moment. I'm just being technically correct. It's an equilibrium reaction, but we don't have to. We can just have that's going to that at the moment. Now we have to balance it. What have we got? We've got 3 hydrogens, well, nitrogen first, remember? We always balance the metals, nonmetals, before the hydrogen and the oxygens. We use those. They get balanced out last of all. Okay. So what do? We say two nitrogens, so we put a 2 there. And now we've got 6 hydrogens, so we're going to put a 3 there. So there my reaction is balanced. Okay. What does it mean? It means I've got 2 nitrogens. I'm going to have 6 of these. 3, 1, 2, 3, because that's going to react there, there. We're going to have each one of these is going to link with an H. Remember we did that in the bonding. Okay. So now let us look at this scenario. Now let's bring in how much of what are we going to put in, and how much do we need? Because when we're going through this kind of problem, and I'm going to rewrite it over here, we don't want to, if you think about it, let's say in our previous problem, instead of putting in 500 mil, we only put in 250. We're not going to get the product at the end that we thought, are we? We're not going to get a batter. We're going to get like a dough sitting there. So we've got to mix everything in the right ratio to get what we want out. Right? Otherwise, we don't get the end product that we thought we were going to get. We get something different. Same with cooking. If you don't do it right, the cake doesn't come out properly, does it? It comes out either sunken, or it tastes different, or it just didn't gel at all, whatever the case might be. So everything is mixed in a specific quantity. That is because we need to make sure that each electron's got its parking spaces that it needs. Okay? Now, let us just take our nitrogen and hydrogen reaction, okay? And I know I'm going a bit slower on this than many of you like, but I think it's worth just recapping this just a bit. So we say, right, nitrogen plus hydrogen, gas, going to NH3 as a gas over here, and we balance it out. 2 of those gives us 6. We need 3 of those, right? Now, this here is our formula. Now, how many of this? There's put down mole ratio over here. Essentially, this is the recipe, isn't it? It's 1 cup of that plus 3 cups of that gives me 2 cups of that. Right? Isn't that the recipe? That's what we're saying over there. It's just that we don't use cups, we use moles. So it's 1 mole plus 3 moles gives me 2 moles. But basically, it's a bucket. If I put 1 bucket of nitrogen, 2 buckets of that, and I'll get 2 buckets of that, right? If you have a problem saying, well, how does 1 plus 3 give 2? Think of it like this. If I put 1 cup of water in a saucepan and 3 cups of sugar, okay, and heat it, I can get 2 cups of syrup, okay? It doesn't necessarily have to equal a balance at that. Where does it have to balance? At the mass level. Because why? Well, if you're going to put so many grams of flour, butter, sugar, eggs, whatever you're putting in, the mass at the end of the day that you've put in there is conserved. Because if you've put X grams in, you get X grams out. Granted, I'm ignoring the fact that when you bake it, we lose mass because we lose water. Okay? But if I measured the situation, and we said, for example, right, let's go into our oven, we put the cake, and we've got 2 kilograms in total there. We put it into the oven over here. We put our 2 kilos. Then we're in the oven, and I take the steam that comes out of the oven with a pipe, and I measure the amount of steam that comes out. Guess what? I am going to have so many grams. My cake comes out at 1.8. I'm going to have 0.2 kilograms of steam that I've caught, of water that's boiled off, right? That mass must be the same, because mass cannot be created nor destroyed, changed from one form to another, which means we change the state. Okay. let's go back to our thing. Now, in this we say, right, okay, that's the recipe, the mole ratio. The next thing is we draw a line under that. You can even put the mole ratio in a different color if you wish, just to remind you that you don't use it straight off. The next situation is to say to ourselves, okay, what are we given and asked for? Okay? What are we given and what are we asked for? Let us say, they say to us that we put in 100 grams of hydrogen. All right? 100 grams of hydrogen, and they want to know how much ammonia and how much nitrogen do we need. Okay? Well, let's work it out. Okay. First thing we do, molar mass, right? Obviously, we're only going to do the molar mass of what we asked for. What's the molar mass of hydrogen? Of a single hydrogen atom, right? Its molar mass is 1. But because hydrogen is diatomic, the molar mass of this is 2. Okay? That's a sticking point that everybody has, right? So I say molar mass of H2 is 2 grams. Now, here's where we can 2 grams per 1 mole. 2 grams per mole. All right? In other words, if I weigh out 2 grams of hydrogen, I've got 1 mole. Right? Nitrogen, okay, I think is 14 is nitrogen on its own, times 2 is 28 grams per 1 mole. Agreed? Okay? Just check. They don't say over here in this one. Periodic table, normally at the back, but anyway, I'm fairly sure of that one. All right, now let's look at the molar mass. Now, what I like to do is I like to draw a nice double line down there. Okay, it helps me to think about when it gets to electrochemistry, because this is where the magic's going to happen, isn't it? Up until this point, we've got no product. This side of the wall, we've got product. This side of the wall, we've got reactants. And let's look at the molar mass of ammonia is going to be, sorry, that's a bit of an ugly, I was just trying to make that a nice 3, okay, NH3, that's going to be 3 grams plus 14 is going to be 17 grams for 1 mole. Okay, the next thing we say, right, number of moles. Now, this is where it goes pear-shaped very often. How do I work that out? Well, you can remember the formula, right? But then ask yourself the question. Firstly, I can't work that out there because I don't know how much nitrogen I've got. So I have to start with the hydrogen, don't I? I've got the most information. Remember, electric circuits, anything in physics, same in chemistry. Yeah, we start where we've got the most info and we work outwards, okay, from there. Okay, 2 grams is 1 mole. We have got 100 grams. Therefore, how many moles is that going to be? Can you see the ratio? 2 as to 1, 100 as to, how do I get it? I'm going to say, right, I have to say 1 mole is 2 grams. Therefore, 100 is going to be, and we divide it by 2. So we're going to get, okay, right, 50 moles. Everybody happy with that? Okay. So let's check the ratio. I've got here 100 as to 50. How do we get the ratios? We get them to the smallest possible. We divide both sides by 50. 1 as to 2. There's my mole ratio. 2 as to 1. Now we say, okie dokie. At this point here, we apply a recipe. Next one, apply recipe. Therefore, we say, okay, 50 moles of that, right? And now this has got to react in 3 to 1. So how many moles? How many moles? Remember, we don't know, and we don't know. But what do we know is we know that it reacts in the ratio 3 as to 1. Right? In fact, let's keep it in red. Well, I've got 50 moles here. So therefore that must be 3 times that one, isn't it? Because I must have a ratio 1:3. So I would divide this by 3 to get that, and it's 50 divided by 3. 50 divided by 3 is going to be equal to 16.6667 moles. Let's check. Is my ratio 1, 3? Divide that by 16.67 and divide the 50 by it as well, and we get 3. So 1:3, right? I'm keeping the ratio. Therefore, how many moles of this do I get? Well, it must be in the ratio 3:2 or 1:2. So if it's 1:2, I must get 16.667 times 2, right? Which is 16.666 times 2 is going to be 33.3 moles of that. Now, we say, right, how many grams is that going to be then? If that is going to be, and we'll do a few of these, don't worry, until you get comfortable with this. Okay, because this is a critical section. How many grams is that going to be? Well, 16 moles. Now I go back and I ask myself, 28 grams is 1 mole. So I write it down. Just look at my logic here. There I've got 28 grams is 1 mole. Therefore, just move myself slightly up. Therefore, if 28 grams is 1 mole, I've got 16.666 moles. So how many grams have I got? 1 is 28, so 16 must be 28 times that. Right? And that's 28 times 16 is going to be equal to 466.66 grams. Okay? Remember, I started with 100 grams here. And how much? Just extend my double line. 33.3 moles, right? 33.3. We said, whoa, hang on, how many grams? Well, 17 grams is 1, and I've got 33.3. Therefore, I work back. It's going to be moles. It's going to be 17 times 33.333 is going to be equal to 566.666 grams. Can you see here, if I add these two, I get that. Conservation of mass must be. Let's divide everything through, okay? And it won't work for the grams, right? I was going to say, just ignore that one. Okay, we do that in a different section. So what we can see here is that, what do we start off with, right? We start off with the balanced chemical equation. Underneath that, we write the recipe, which is the number of moles, right? Under that, we write given or asked for. In other words, where do we start? We start with the given, and we work out towards the asked for. The second, we calculate the molar mass. The third, we calculate the number of moles. When we've got the number of moles, we can apply the recipe, because now we're counting in moles. We're counting in atoms, electrons, right? That's why we do it. That's what we do. We count in electrons, right? Therefore, we can apply the recipe at mole stage, not before. When we apply the recipe, it's basic ratios. It's a ratio of what we're given to the other elements in the scenario, okay? Don't worry about limiting reactants or anything like that yet. We're going to get to it, okay? All we've got to say to ourselves is, this is where we're going and measuring the quantitative aspects. Next time, we're going to do ones involving gases, and we're going to build up towards limiting reactants, okay? We're even going to start looking at electrons, because, hang on, 1 mole of electrons contains Avogadro's number of electrons. Think about that, okay? It's going to take us to places like, hey, electroplating, spray painting. Takes us into those areas as well. so that we can try and visualize why we're doing this, make it real. What's it for? Why am I bothering to do all of this stuff? We're going to try and now start bringing in more and more life examples of where this is used. That's the next step.